All right, welcome back to the Explainer. We're going to tackle a really common and, let's be honest, super frustrating problem that a lot of Python developers run into. So picture this. You've got your Flask app, it's running great, it's stable, and then you decide to add some real-time magic, maybe something like a video chat. And all of a sudden, it just falls over. It crashes the moment you put it under any kind of real load. We're going to dig into exactly why that happens, and more importantly, how to fix it with a surprisingly simple but incredibly powerful solution. So yeah, let's just frame this as the mystery that it is. You've spent all this time building a really solid web app with Flask. It's reliable, it does its job. But the second you introduce something like WebRTC signaling for a video call, these connections that have to stay open for a long time, your server just can't handle the traffic. It's a total head scratcher. So what is actually going on here?
Well, it turns out the culprit has a name. It's a classic scalability wall known as the C10K problem. And yeah, that 10K literally stands for 10,000 concurrent connections. See, it's this fundamental roadblock you hit when you take an architecture that was built for quick, in and out requests, and suddenly you try to slam it with a flood of connections that need to stay open. It just wasn't designed for that.
All right, so here's how we're going to break this down. First, we'll look at the concurrency crisis itself. Then, we'll pinpoint the blocking bottleneck that's causing all the trouble. After that, we'll see the asynchronous advantage, how Quart offers a seamless upgrade path. And finally, we'll look at the numbers, the performance payoff.
Okay, first up, the concurrency crisis. Let's really get into the nitty-gritty here, examine the crime scene. What is actually happening under the hood of your server when it gets hit with thousands of these real-time connections all at once? So, this really gets to the heart of it. WSGI, that's the Web Server Gateway Interface. It's the foundation that Flask and many other Python frameworks are built on. And it was designed for a very specific kind of web, a stateless one. A user makes a request, the server does some work, sends a response back, and boom, the connection is closed. Simple, efficient, and perfect for that job. But WebRTC, that's a completely different beast. It needs those connections to stay open. It's stateful, and that fundamentally breaks the entire model that WSGI was built on. And the consequences here are, well, they're pretty brutal. Think about it. With this one thread per user model, if your server has, say, 16 threads, it can handle exactly 16 concurrent users. That's it. User number 17? They're stuck waiting in line. Now try to scale that up. You want 10,000 users? You'd need 10,000 threads. It's not going to happen. The memory consumption alone would be insane. We're talking 4 to 8 megabytes per thread, not to mention the overhead for the operating system trying to juggle all of that. It is, for all intents and purposes, a complete dead end. Okay, so let's dig a little deeper. We need to investigate our prime suspect, the thing that's really killing your performance here. And that suspect has a name: blocking I/O.
Now, this is the really critical piece of the puzzle. Your server spends almost all of its time just waiting, right? Waiting for a user to send the next message, waiting for a database query to come back. And in a blocking model, a worker that's waiting is completely useless. It's like a cashier at a grocery store who stops serving everyone in line just because one customer is taking a long time to find their wallet. It can't do anything else. It's totally tied up, blocking everyone else behind it.
And this table really shows the fundamental mindset shift you need to make. With traditional threads, you have what's called preemptive multitasking. The operating system is the boss. It decides when to stop one task and start another. These are heavyweight OS threads. But with an event loop, it's cooperative. The application itself says, hey, I'm about to wait for something, so I'm going to yield control. It's working with lightweight task objects, not full-blown threads. And for I/O-bound work, which is mostly just waiting, this cooperative approach is just wildly more efficient.
So, we've identified the problem, we've found the culprit, now it's time for the breakthrough. This is what changes the game completely. This is how we solve the case. And here it is. The key insight is a new standard called ASGI, the Asynchronous Server Gateway Interface. Think of it as the modern async successor to WSGI. It's built from the ground up for tools like Python's asynchro. And here's the magic. Instead of fighting against waiting time, it actually embraces it. It turns waiting into a feature. When a task knows it's about to wait for the network or a database, it just tells the event loop, hey, I'm going to be a minute, go work on something else. And the loop does exactly that. The impact of this is just huge. I mean, the cost of a connection that's just sitting there, waiting,
plummets. Instead of tying up a whole resource-hungry operating system thread, it becomes just this tiny little object sitting in your application's RAM. And that is the secret sauce. That's what allows a single process to juggle tens of thousands of connections without even breaking a sweat. Okay, so knowing the solution is one thing, right? But the next question is always, oh man, do I have to rewrite my entire application from scratch? And nobody wants to do that. Well, this is where the hero of our story comes in. This quote just nails it. Think of your application like a car. With Quart, you're essentially swapping out the engine. You're taking out that old, sputtering, blocking engine and dropping in a brand new, high-performance asynchronous one. But, and this is the beautiful part, you get to keep the chassis, the steering wheel, the dashboard, everything you're already familiar with. That's the genius of Quart. It's an async framework, but it has a Flask-compatible API. And just look at how similar the code is. It's pretty amazing. On the left, you've got your standard Flask app. On the right, the Quart version. What's changed? Well, you change the import from Flask to Quart, you add the async keyword in front of your route function, and then for any I/O call, like talking to Redis, you just put a wait in front of it. That's pretty much it. The structure, the logic, the way you think about your routes, it all feels incredibly familiar. So here's your roadmap to make the switch. It's a simple 4-step plan. Step 1, swap the import. Easy enough. Step 2, refactor your routes to be async def and await your I/O calls. Now, step 3 is absolutely critical. You cannot skip this. You have to replace any synchronous libraries. If you're using something like requests, you need to switch to an async version like HTTPX. Why? Because a single synchronous call can poison the well. It will block the entire event loop, and all that async goodness just goes out the window. And finally, for any heavy CPU work, you can offload it to a thread pool. All right. We've talked the talk, we've swapped the engine. But what does that actually get you in the real world? Let's look at the numbers, the hard data from actual benchmarks. 9 times. Let that sink in for a second. A 9x improvement in raw throughput, how many requests you can handle per second, on the exact same hardware. That is a massive gain, especially when you consider this is from a focused refactor, not a complete ground-up rewrite. And believe me, the benefits don't even stop at just pure speed. I mean, this chart just says it all. You can see the old stack, Flask with Unicorn, it just hits a wall at around 1,500 requests per second. It can't go any higher. But the new asynchronous stack, Quart with a server like Unicorn, it just keeps going, handling an order of magnitude more traffic. The performance gap is just enormous. And here is the other huge payoff, efficiency. Look at the memory usage. To handle the same 1,000 concurrent users, the old Flask model chews up over 4 gigs of RAM. The Quart model, it's using less than 500 megs. That's a huge difference. We're talking about a direct impact on your server costs, your infrastructure bill. You can do so much more with so much less. So we've gone through the whole investigation. What's the big takeaway here? What's the final lesson for how we should be building our apps going forward? It really comes down to this new mindset. In the old world of real-time engineering, idle time was your enemy. Every waiting connection was a thread you couldn't use for something else. But with an async framework like Quart, you flip that on its head. You turn that idle time into your greatest scalability advantage. It becomes an opportunity for insane efficiency, letting one process do the work that used to take a whole fleet of servers. Look, the real-time web isn't going anywhere. With things like WebRTC, live streaming, and real-time AI, it's only getting bigger. So the real question you have to ask yourself is my application's architecture actually ready for that future? Well, hopefully this explainer has given you the blueprint to make sure the answer is yes.